Hi there, this is Module 3, Lesson 2, Sampling Distributions. If we look at the title of this lesson, Sampling Distributions, we do notice that we have seen each of these words individually. Distributions is a word we used a lot in the early part of this course and helped us to describe how the data was spread out along the different values the data could take on. Sampling is something we remember when we would choose a smaller group from a population. Now, by combining these two words together, we're going to be looking at data that is comprised of samples and their results. What I mean by results is maybe I took a sample and from there computed a proportion. Or possibly I could draw a sample from a population and compute a mean. These proportions and these means are going to be used as sample data. Why don't we take a look in Statcrunch at an application to better understand this concept. Statcrunch has a neat applet. There's this applet button, which we haven't used, this applet tab yet, and it's called Sampling Distributions. And it's going to allow me to hopefully give you a hands-on demonstration of what a sampling distribution is. So first I'm going to leave my population at uniform, and I'm going to set my lower bound to be 17, and my upper bound to be 35. I'm going to press compute, and it's going to give me this pop-up box. Now what this pop-up box represents is a fictitious population. Notice how it says population down here. Now this is a fictitious population where the lowest value is 17 and the highest value, as I indicated, was 35. Now I want these to represent, let's say, students' ages. Now it's a very unique population because of the flat nature of this distribution. That means there's just as many 34-year-olds, let's say, as there are 20-year-olds, as there are 27-year-olds or 27-year-olds in this data set. So each age has just as many people in it as the next. So thus we have a flat distribution. Now, what I want to do is I want to draw a sample at random from this population. Let me change my sample size to 5. So we're going to randomly choose 5 students. Up here I'll hit one time, and there are 5 students. As you can see, these little blocks represent the sample values. 2 that were less than 20 years old, 1 somewhere between 20 and 25, 1 between 25 and 30, and then 1 that's older than 30 years of age. If you add all of those up, that's what this next graph is. It is the mean of these 5 ages. So if you add up the 5 ages of these students, the average, as you can see right here, this average is 24 years of age. Now, the average of our population here, the population I made up, is 26 years of age. So if you add up all the values in this and divide by the number of people, the average age of a student in this population is 26 years of age. Let's draw another sample. See how the computer randomly selects them. So you can see this sample was much different than the last. You have a couple of older students and a few younger students here. Now the average age of these 5 students is here in the middle, I should point out, is 28.8 years old. And then it dropped. That green box here is 28.8. Let's try another time. So these students were more in the center of the data, 5 of them, and they had a mean of about almost 27 years of age, and here it goes right here. That's that mean in the middle there. Last time we'll do it slow like this. So you had a couple of younger students, middle of the group, and then an older student, and their mean was 24, which is right here. So this could be a really long process to do it individually. So I'm actually going to press 1,000 times. Now what this is going to do at lightning speed is randomly select 1,000 different samples, take the mean of those ages, and then drop that mean value into this graph down here. So this graph down here is a collection of sample means. Let's do it. Whoa, there it is. So here is our distribution. You can see that we had just a few samples where we had a lot of young students. In other words, that the average was 20. Very rarely did we had a couple of samples over here. You can see the short nature of the bars where the average was up in the 30s. But most of it is right here in the mid-20s as we would expect. Now let's look down here. This tells us that the mean of this distribution is roughly a little over 26 years of age, which is very similar to the mean of the population. You can see that sort of center part here lines right up. They're both pretty symmetric looking, not perfectly symmetric looking on the bottom distributions. I would say bell shape and somewhat symmetric. So this is what happens when we take samples from a population. And what we do, instead of using these 5 values individually, we average them. And we use that average to represent the sample and build a distribution down here. So let's try a different shape. I'm just going to kind of use my mouse to build another fictitious group of students. Okay? Now these students, in this distribution, what would you call this distribution? Skewed to the right. That's exactly correct. So we can see there's most of the population are students in their late teens and early 20s, and then as the ages go up with less frequency we see students. So I just kind of made this up. So the population mean is 21.3 here, 21.3 years of age. And we're going to try this process again. Now, let me see one time. Do it again. You sort of into slow-mo version of this. And you can see it's randomly selecting students. And after they take the 5, they average them out. The average of this most recent one was 23.7 years of age, and it dropped it down here at 23.7. So, let's speed this up. So you can see I did this 1,000 times. Actually, we've done it, if you notice here, 1,003 times, because we did do it 3 times individually. Let's take a look. Again, remember that mean here was 21.34 years of age. Look at the mean here, 21.33, pretty darn close. The standard deviation up here was just over 3 years of age, and you can see down here it's just under a year and a half. So the spread of this data is considerably smaller. You can see it's widely spread out here, but in this distribution it's a little smaller. How would you describe the green distribution? Well, I'll definitely say it's unimodal. It's a wee bit skewed. It's not quite symmetric. So what I want to do here to illustrate something is to increase the sample size and see how this changes the shape of our green histogram on the bottom. I'm going to change it to 30. Nice sample of 30. Let's do it one time. There you go. There's the 30 students that fell out. If we counted those boxes, there would be 30 of them here. And some ages duplicated themselves, and some they had single ages. And the mean of this is 21.8, and of course it dropped it here at 21.8. Let's do this 1,000 times. Wow, look at this. The mean again, 21.3. Look at the mean down here, 21.3. So the mean of the population is being replicated here in the sampling distribution. Look at this curve. It is unimodal and symmetric. The standard deviation up here was just over 3 years of age. Down here is just over a half of year of age. So the mean from the population and the mean in the sampling distribution, so the mean at the top and the mean in the green, are essentially the same. But the standard deviation shrinks considerably. Let's try a different distribution. I could skew this to the left, and I think you would believe me that the same phenomena would happen. Let's try a bimodal distribution. This is an interesting set of students where we have 2 groups of students here, probably a younger set and an older set of students, thus having this sort of bimodal effect here. But it doesn't matter what the shape of this data is. I'm just having some fun. This is 25.4 years of age is the mean of this group of students. Now let's grab a sample out. Let's keep it at 30. There's our first sample, 25.4, and they drop it here. Second sample of 30. See, it's a random sample every time. Third sample. Now let's fast forward it to 1,000 times. Now you can see that we have yet again another unimodal symmetric data. Now again, this is a collection of means. So we take the sample, and instead of using them individually, we compute a mean of these 30 and let that represent down here. And what this green curve tells us is how sample means behave. They tend to follow a normal distribution. Let's note again, 25.4 years of age, 25.4 years of age, or 0.5. So very close. The mean of this distribution is similar to the mean of this distribution. Again, with the just over 4 years of age and standard deviation, and right about 3/4 of a year down here. So it shrank again. Last one. So I'm going to do my best to try to draw something that sort of has a normal shape to begin. So some distributions we find already exhibit a bell shape to them when you get them. Now, this is not perfect, but I think it's good enough. A little tricky to do this with my mouse. There we have it. There's a bell-shaped distribution. There we go. So it's about almost 25 years of age here. And if we pull a sample out, another sample, do it 1,000 times, and you can see here that the mean of this distribution again lines up exactly with the balance point and mean of the population up there. Standard deviation here is quite large, at a little over 3 years, and down here just a little over half a year. So I want to go back to the PowerPoint and kind of talk in general about what's going on. Here is something in statistics that we call the central limit theorem. And it tells us that when a random sample of size n is drawn from a population with a mean mu and a standard deviation sigma, now these are just our population symbols, for mean and standard deviation, its sample mean, x bar, has a sampling distribution with the same mean, but whose standard deviation is sigma divided by the square root of n. So this is the population you started with, and I just chose a normal one to illustrate this. Mean, standard deviation. If we sample from here, repetitively samples of a particular size n, and compute a mean, that is an x bar here, that if we gave a histogram of the means, they would also have a bell shape. The mean of the population will be very similar to the mean of this distribution down here, but the distribution on the bottom would be a lot skinnier. In other words, the standard deviation shrinks. It shrinks by dividing it by the square root of n. Now, what's interesting is that this phenomena we saw of the standard deviation shrinking down and the mean staying pretty much similar, that happened for the uniform distribution, the skewed distribution, whether it's right or left, a bimodal distribution as we saw, and the normal distribution. Now, to ensure that we end up with the nice unimodal symmetric model, that is our normal model, for these first 4 distributions, the ones that clearly aren't that shaped to begin with, you have to have around 30 or more in your sample to see this phenomena happen. But the exception is with the normal distribution. If your data has a bell shape to begin with, your sample can be any size. Small, large, you're still going to end up with a sampling distribution of a mean that's approximately bell shaped.